Probably don't need my safety glasses while I'm standing in front of the camera, though. All right, it looks like it is going live. Let me mute that. Down here. All right. Yesterday, I think we ended with a discussion of, right, I'm not screen sharing, am I? No, okay. Yesterday, I think we ended with a discussion of making a control chart and also looking at the distribution of the data here. Is that correct? Does everybody remember something like that?
I remember the chart. I don't know if you ever drew it, but I remember the chart.
Where the heck is my Zoom controls? There you all are. All right. And so as we make a part, and so say the dimension, say again? All right, so as we're making a part, there's typically some critical dimension that we're trying to control. So we need to make sure that, for example, on these cylinders that you guys have either made or will make today, on the cylinder, there's a couple of important dimensions. We care about this outside diameter right here. And we care about that because it has to fit in the Y block, and then the strap that holds it together has to fit over the top. So we care about that dimension, but it's not having it vary by up to several thousandths of an inch won't affect the ability of the engine to run. But the inside diameter here, where the piston slides in and out, if we don't control the difference in diameter between the piston and the cylinder to within about 8/10 thousandths of an inch, so 0.0008, then the engine won't run. So that's a critical dimension. And so that's something that we might check every part coming off the machine, or if we know the machine's running in control, we might check every 100 parts or every 1,000 parts coming off the machine. It depends on how quickly we expect the tools to wear out. And so when we do that, as we go, when we measure a part, we put the dot on the plate, on the plot. And we measure a part, we put the dot on the plot. And it builds this graph that shows over time how that diameter or whatever dimension is that we're trying to control, how that varies over time. And so if this is our upper control limit and this is our lower control limit, just looking at the plot, would you say that this process is in control?
Yes.
Yeah. So just intuitively, we understand that this process is in control. And that happens, and when you do that, if you simply plot these dimensions in a histogram format over here, you can see the distribution of that. And so what we see is most of them are close to this mean value. So we could plot a mean value here, right? The mean is just the average. So we could get a mean value here. And so we can see that most of the values are close to that mean value. As you get further away from the mean value, either big or small, you end up with fewer and fewer values that are out there. And so this gives us a normal distribution, and we look at this a lot in statistics and doing calculations. And so, can somebody tell me what the standard deviation is? Did we talk about this yesterday? We know the mean is the average. And so the standard deviation is basically a measure of, what's the best way to explain it? It's a measure of how close is the average point to the average value. And so we can calculate a standard deviation, and there's formulas for that. You can look up the formula for standard deviation, but you can calculate the standard deviation for the value. And you can get and we use the symbol sigma for that. And so you could have plus or minus 1 sigma, 2 sigma, 3 sigma. And so the range from -3 to +3 is 6. Say again? Did somebody say? Is it hard to hear? Let me turn the gain up on the mic a little bit. So as we do this, so if all of our data points fall in between this plus or minus 3 sigma, then our process is definitely in control. And so if you get out here, I never remember these numbers off the top of my head. When I need to know them, I look them up, and I didn't look it up for this lecture. But something like 99.999% of the parts are in spec out here at plus or minus 3 sigma. As you go out another sigma, you get even more of the parts in spec. So this is good. Now, what other circumstances could happen with our data? What else could happen? So this shows an in control process. We're making good parts. What if
Could be skewed in one direction.
What if our data looks like the orange lines here? So some of them are inside the control limits, some of them are outside the control limits. So what we did is we fattened the curve, basically.
Professor, although I can see it, the orange does not really show up very well on the whiteboard camera here.
I kind of thought, oops, I don't want to close the Zoom meeting. I just want to get this window out of the way. Yeah, let me try a different color. Does the green show up any better?
Yeah.
All right.
A bit.
So green line, and I'll just sort of, but our green line sort of, our control chart, we expanded outside our control limits. We're outside our control limits here. Now, our process still makes some good parts. In fact, it makes mostly good parts, but enough of them are outside. So what do you have to do in order to still ship your parts to your customer if you have this experience?
Test more of them.
You have to measure each part before you ship it, right? So you ship the good parts, you throw away the bad parts, you scrap the bad parts. So you can still ship, in this situation, you can still ship parts to a customer, but it's much more expensive. Now, what else could our data do? I'll try blue, see if blue shows up. What if our data was like this? What if it was oscillating around that upper control limit instead of around the mean?
Then there is something fundamentally wrong with how
Right?
you.
So the distribution would look something like this. Upper control limit. Can we still ship parts to our customers?
No, we need to figure out what is fundamentally
But we
wrong.
still can ship these parts to our customer, right?
I suppose
But
that's a
it's
lot of
much
waste.
more expensive because the scrap rate would be much higher.
What happened to reduce waste?
Yep. Well, that's we're looking at, yeah, that's where we're getting, right? So all of these possible situations could exist. What's probably wrong here in the blue graph?
Tool offset.
Probably we get the tool offset wrong, right? A systematic error like that, we should be able to fix pretty easily by making an adjustment at the machine and shift the mean to the right place. The one that's really hard to fix is when our data is out here like this. When our machine is actually not capable of making the parts that we want to make. So a shifted mean we can usually fix. And so if I go back to my screen sharing, this one, no, this one. So this is what gets us to calculating the machine's capability. And there's two different capabilities shown on this slide. There's this CP or CPK, and there's a PP and the PPK. And I just want to quickly look at the difference between the formulas here, because they both include this upper and lower control limits. They call it the USL and the LSL. They both include that. You can see this if you calculate the CP or the PP, you divide by 6 sigma. And so the sigma is the standard deviation. So it's plus or minus 3 typically is what we're seeing when we say 6 sigma. And so in CP, it's 6 sigma with a little hat above the sigma. And in PP, it's 6 sigma where the sigma is calculated from the data. The difference between the sigma with the little hat and the sigma that's calculated from the data is the one with the little hat. You look it up in a table, and it's based on what the distribution should be for that type of data. And the one that doesn't have the little hat is from the data that you actually calculated. There's debate about which measure is better, and they both have their place. So what we're going to do in the class, and there's a quiz question about that, we're calculating the PP, which is just like the CP, except it uses the actual data and the standard deviation of the actual data as opposed to a value that you look up in a chart. And we're doing that because I believe that the PP and the PPK have more information. There's a really great video that explains this. And I don't want to try to explain it. The video is on the next slide, but I think we're going to skip over that. I've got a link to it in the course notes on Canvas now. Where's the thing? Where's Canvas? There it is. Let me drag Canvas over. So I've got a link to it in the week 2 thing down here next to refresh. Next to where it says the quiz. And so down here, this is a link to that YouTube video. It's about 7 minutes long. It's a guy that teaches this stuff and he focuses on this and he explains it really well. So the CP, the PPK, the CPK, PPK, CP, PP, how many times can you say PP on video and not laugh? Depends how small your kids are. These things are in the quiz. We're going to be talking about it. What I really want to do, though, is I want to move on to the acquisition of the information. And so we said we're going to talk about quality and metrology. And so quality is about shipping to your customer the thing they need when they need it and meeting all of your customer specs. Basic overview. But you can only do that if you're able to measure the things that your customer wants. So you can only control your quality if you're able to measure the things that your customer wants. At my manufacturing company, one of the first things that we do when we're quoting a new job, so when somebody gives us a part, they want us to tell them how much is it going to cost to measure or to make these parts. Of course, we have to figure out, the cost of the raw materials and the cost of the processing time and all those things for us to do that. But we also include what's our measurement plan going to be and what's the cost of that measurement going to be. And so we always include that information in calculating the cost of making parts. And so in the chat, let me open up I'm going to stop screen sharing. Stop the screen share. In the chat, I would like everyone to take, let's take 90 seconds, a minute and a half. Think about it and then write your answer in the chat. But the first question is, and when I'm in the classroom, we do this on little index cards that I pass out to you and you pass them back. So this will work exactly the same way. In the chat, tell me, why do engineers measure things? And why do scientists measure things? So why does a scientist make a measurement? Why does an engineer make a measurement? So there's 2 questions to answer. And just go ahead and type your answer in the chat, but think about it for a minute before you start typing. And we'll say, we'll give it about 90 seconds before we reconvene and answer those questions. So the question is, why do engineers measure things? Why do scientists measure things? All right, did everybody have a chance to type something in the chat? Looks like a bunch of people did. Can somebody start at the top and just shout out the answers to me, and I'll make some notes on the board. I'm seeking a volunteer because I can't look in both directions at the same time.
Engineers. Oh, go ahead.
Go ahead. Okay. The first one says, engineers need a clear measurement so something doesn't break.
Yeah, go ahead. Keep going.
Engineers measure to check the value against the known value. A scientist measures to find the known value engineers use.
Go ahead.
A scientist makes a measurement in order to better understand something. An engineer makes a measurement so they can be sure something operates how they want it to and to verify that something will run safely. Scientists make measurements to figure out why things work. Engineers make measurements to make sure things work. A scientist makes a measurement to discover something, and an engineer makes a measurement to create or build something by design. Scientists measure data to understand a system. Engineers measure parts to fit them together. Scientists measure and discover constants and standards. Engineers measure things to check accuracy. Scientists measure things to understand something. A scientist makes a measurement to collect original data. An engineer makes a measurement to confirm why that data makes sense. Scientists measure things to determine trends, and engineers measure things in an attempt to control or change pre-existing trends. They both measure so they get what they expect. Small errors in measurements add up and cause problems in the long run. An engineer measures to check their work. A scientist measures to understand how something works. Scientists make measurements as observations for data. Engineers make measurements to compare their manufactured part to the dimension of the part they modeled. Scientists measure to prove or disprove a principle they are testing. Engineers measure to make sure what they are making follows the proved principles by scientists.
We call that verify.
Engineers measure things to make sure it was made right or to find necessary dimensions for design. Scientists measure stuff to gather data in pursuit of learning about or researching something. An engineer makes a measurement to ensure what they are making is what they need. A scientist makes a measurement to ensure that they understand what they are studying. Scientists measure to find an unknown value. Engineers measure to check a known value on a specific part. Engineers measure things to make sure what they are developing functions correctly. Do you really want all of these? Only about halfway
No, we're
through.
good. I think we've got a representative sample. And I think our representative sample shows a pretty clear trend. One, that you guys aren't dumb. So you actually understand sort of the difference between science and engineering, right? And so most of the answers about engineers are about checking to see, did we do what we meant to do? We're going to control our system. We want to confirm things. We're checking because we don't want things to break. We want to verify, make sure things fit is a verify. We're trying to create something. I want to circle this word accuracy. We're going to talk about this in depth. And I put this get what you expect in the middle because the person said that they both measure to get what they expect. But in reality, if you think about it, I think we've all got this in our mind, is scientists are measuring things to try to understand something that they don't already understand. They may have a theory and they may be trying to verify the theory, but what they're trying to do is they're trying to document what is. And engineers are often measuring things, especially when they're in this create and build state here. They're measuring things to find out what could be. One of my friends, he likes to say that that scientists ask the question why, and engineers ask the question why not. And so, but at the same time, it is impossible to be a good engineer unless you are also a good scientist. It may be possible to be a good scientist without being a good engineer. It's probably not, but it's certainly impossible to be a good engineer without being a good scientist. And so when we do these modeling exercises, we're talking mostly about science. So that's about our spreadsheets and stuff like that. And when we're doing our metrology, so when we're measuring things, we really have to understand the science in order to be able to use the data effectively to control our processes, to build good things. All right, so we have the word accuracy. What does it mean to have an accurate measurement?
They're close to the expected value.
So accuracy is close to the expected. This marker doesn't work anymore. Does accuracy mean anything else? How do we decide what's expected?
Well, usually you're comparing it to a model.
I couldn't hear you.
Usually you're comparing it to like a CAD model.
So you're comparing it, so you may be comparing to a CAD model. And so in this sense, we have a specification, we're making a measurement to determine if we've met the specification. But what does the word accuracy actually mean? If we define the word accuracy, it doesn't, we may need accuracy to compare to a CAD model, but I don't think accuracy means compare to a CAD model. It may mean be close to the expected value.
Accuracy would be the closeness, or if lack of accuracy, lack thereof, of a measured value to the known, accepted, true kind of value.
Are you reading a definition?
No, I just remember from old science classes in high school.
Okay, all right. Because that is very similar to the wording of the definition in the International Standards Organization definition of accuracy. Accuracy is the closeness to the true value. Now we can debate what it means to be the true value, but by definition, the accuracy of our measurement is how close is our measurement to the true value. What's precision? And this precision, you can think of it as precision with respect to target practice. You could think of it as precision with respect to playing darts. Anybody ever play darts? I used to be really good. I'd be there. And if you play darts, I was a master at the game cricket. And I was often very precise, but not necessarily accurate. And you have to be both precise and accurate to win at marksmanship or darts. So what is precision?
Precision is the closeness of a set of values to each other.
The precision is the closeness of the values to each other, right? So in both darts and marksmanship, if somebody's very precise but not accurate, you want to still compliment them because it's nice to compliment your friends in a friendly game. And so you'll have to say, nice grouping. Because you put all the shots real close together. It's just, it was above the target's left shoulder. So you had a nice grouping, but you didn't hit your target. All right, so accuracy is closeness to the true value. Precision is closeness to each other. How do we know what the true value is if we're measuring something?
If it's a scientist, we might not necessarily know the true value, but if we're engineers, then we should have it in our CAD model.
Well, no, because, and I wanted to get to this. This is getting what you expect. So if I take my measurement tool, it's funny, I'm in a room full of measurement tools. Let me see if I can grab one. So I have my measurement tool here. It's a digital caliper. It opens and closes. It's a little bit dirty. And I can measure, let's say, the diameter of my cylinder. And I get 1.101 inches. What's the diameter of my part? Well, let me try again. No, the battery's dying here. And I get 1.0995. It's possible there's a reason this was in here. And now I get 1.101. I measure it again. And I get 1.137. What's the diameter of my part? It's all the same part. It's the same measurement tool. It's the same operator. I will admit I was on purpose doing a bad job. But what, do we know the diameter of the part? Do we know which of those numbers was the most accurate? We can't know which one was the most accurate if we don't know the diameter of the part. Would you believe that? Okay. So if we make a bunch of measurements of something, there will be a mean value, right? As long as we make more than 2 measurements, we can calculate a mean value. So if we make a bunch of measurements, there will be a mean value. There will also be a standard deviation. There will be an average distance of each individual measurement from the mean value. So we'll have a mean value, we'll have a standard deviation. Can we determine what the true value is? Is the mean value the true value?
It could be really close.
It's certainly related to the true value, right? Mathematically, it's related to the true value somehow. Now, what if I took a measurement standard and I also used my calipers to measure the measurement standard the same number of times? And I know what the true value of my measurement standard is because it's certified. And the people that certified it, they measured it by bouncing light waves off of stuff and knowing what the speed of light was. So I can measure my measurement standard and I can see if when I measure my measurement standard, I get the same kind of variation. So I have the same kind of standard deviation. And I know that the true value is here and my measured value is here. I know that I have a linear offset between my measurement tool and the true value. So I can apply that linear offset here, and I could then know what the true dimension of this is, except when they send me my measurement standard, and I've never had a brown one before, but when they send me my measurement standard, they say, the diameter of your measurement standard is this, plus or minus this amount. Because we know that our measurement system also has some uncertainty. And we've estimated our uncertainties, so the true value is within this range. And so now I've got some uncertainty in my measurement standard. I've got some uncertainty in my measurements because they vary all over the place. And so it's kind of like wearing a mask. I don't know that my wearing a mask is going to protect you, and I don't know that my wearing a mask is going to protect me, but I have faith, right? I have faith that it's better than not wearing the mask. So there's measurement uncertainty contributes to how close we can be to having an accurate measurement. Now, if your measurement's all over the place, then maybe you need a better measurement tool. How, with my calipers, could I decrease the uncertainty very easily? The fastest and easiest way to decrease my uncertainty in my measured value. So these calipers will measure to 1/10 of 1,000th of an inch. And very often, and so that's, so say we're looking for 1 inch, we get 1.0001. And then the next time I get 0.0003. And the next time I get 0.0002. And then maybe I get a 1. And maybe I get a 0 again. And maybe I get 0.99999. Too many nines. So when you make measurements like this, they tend to vary at that last decimal place often. If I want to decrease my uncertainty, what do I do? I could just not report the last decimal place. Every time I measured it, it was 1. So one way to decrease your uncertainty is to not need the same resolution. I wanted to use the word precision the way people use the word precision in layman's terms, but it's not the right word to use here because, again, precision is how close these numbers are to each other. Accuracy is how close this is to the true value, and resolution is how many decimal places we have. So if we reduce our resolution, we can increase our certainty or decrease our uncertainty. Okay, let's go back to the screen share because I got a couple of things to go through here. We got about 15 minutes. Where's the button for the screen share? Here it is. Screen, this one. And I want to make this one go away. Go back over here, but we're not going to watch the video. You guys can watch the video on your own time. There, where does the data come from? It comes from measurement. We just talked about all this stuff. Come on. Who should do the measurement? Well, it depends. All right, so accuracy, precision, we talked about that stuff. In manufacturing, so let's focus on manufacturing. We can either be talking about science or engineering. There are things that we can measure. We can easily measure lengths, angles, flatness, roundness, diameter, form. So form is the shape, right? And so is there anything else you could think of that you could measure in manufacturing? So we can measure length. If we measure length 3 times, we've got volume. What else could we measure in manufacturing to control our process? Quickly, just type them in the chat window, maybe. I'll open up the chat window and I'll shout them out as you type them. So area is just length. What else could we measure? Mass, we can measure mass, that's not on our list. What else could we measure? Anybody? We can measure time. Density is just a combination of mass and volume, right? We can measure volume, but volume we're measuring length. Pressure, we can measure pressure. Pressure, what's the units for pressure? Force over area, so we can measure force, and we already have the area from length. Yep. Temperature, we can measure temperature. We often have to control temperature, and in fact, temperature often impacts things like all the other measurements. Hardness. To measure hardness, what we do is we take something, we push on our material with a known force. It makes a plastic deformation in our material. We leave a dent in the material after we push on it. It helps if you take something that's really hard and really small when you're doing the pushing, and you look at the size of the dent that it left in the material, and from that you can infer what the hardness is. So yeah, we can measure hardness. We have to measure length and force in order to measure hardness. Aerodynamic drag, so you can measure force again after applying a airflow past something. We can measure conductivity. That's something that's not on our list yet. To measure aerodynamic drag, you'd have to measure force, and that's it. Force. Plasticity, you'd have to know what the wind flow was. Plasticity is similar to hardness. It's like their, well, I guess ductility is the word we usually use. Plasticity would be, I guess, the strain at which elastic deformation becomes plastic deformation. So yeah, we measure that. So there's a lot of things that we can measure. What we mostly measure, nobody had color. We can totally measure color also. I once, as part of a graduate research project, had to build a colorometer, or I called it a colorometer. All right. So there's a lot of things that we can measure. we measure to control our processes as manufacturing engineers, or if we're at the early design phase, we measure to design our parts. So we may do an experiment to see, does the part of this size actually function? But once we're in the manufacturing state, once we're making product that we're intending to ship to customers, we're almost only measuring to control our manufacturing process or to ensure that we don't ship crap to the customer. Measurement uncertainty is going to make it so we don't know if we're shipping crap to the customer all the time. Coordinate measuring machines, a bunch of different things. So we talked a little bit about the things like conductivity. We could measure chemical compositions of things. We can measure how magnetic something is. We could use a microscope and we could look at the structure of the crystals or whatever the microstructure is as they come together. Stiffness, hardness, ductility. So these are all things that we can measure. One of the things that is extremely important to understand, and is often just assumed to be okay, is the surface roughness. So everybody sitting wherever you're sitting right now, you have one of the most often used surface roughness measurement tools in the world. You possess it right now. So you guys are holding up your fingers. Typically we use our thumbnail. And if you take your thumbnail and you drag it across any surface that you can reach right now, there's a signal being transmitted from that surface to your brain. Now find a different surface and drag it across that. Can you tell the difference? Oh, it doesn't matter if you just clipped your nails. I mean, it's not just my thumbnail. The tip of my thumb is touching too. So if you practice this skill and you compare with a reference standard, so you rub the reference standard and then you rub the surface, and you rub the reference standard and you rub the surface, you can get a quantitative, well, it's really qualitative. You can get a qualitative measure of the roughness of that part, which is good enough to control the manufacturing of things like nuclear-powered submarines. So the thumb scratch method is how they check the surface roughness of weldments on nuclear-powered submarines before they put them in the water. Now, as a surface metrologist, I like to rub my thumbnail on stuff to see how rough it is. But in reality, that's not the only way you can do this, right? And it is hard to control the manufacturing process by having Jim or Sally out there rubbing their thumb on every part, because what's going to happen over time? Anybody play guitar? Over time, they develop calluses and their sensitivity changes, right? Sometimes we use a visual inspection to check things before we ship it to the customer. I had a consulting job once where we needed to develop a metrology system to replace a guy named Joe who worked at the end of the manufacturing process line. Joe's job, now the company made golf club shafts. So we're playing golf, right? People buy golf clubs. One of the things they use to determine whether or not they're going to buy the golf club, we got feedback. One of the things that we do to determine whether or not we're going to buy the golf club when we're at the pro shop is we hold it up and we look at it. And if it looks good, that's a mark towards buying it. If it looks bad, we put it back on the shelf. Maybe we pick up another one. Maybe we walk to a new store. So they understood that to sell golf clubs, the shaft had to look nice. And there's a guy named Joe, and his job after the brush finishing process was to look at it and say, yep, that's a good one. Yep, that's a good one. Nope, that was no good. Yep, that's a good one. And he would sort the crap from the good product. Except they got a new guy and he did some statistics and he was looking at the failure rates on the parts and seeing if he could I correlate the failure rate on these parts with anything in the process. So can we adjust the process to reduce the failure rate? And he discovered something very interesting. Any day after the Red Sox lost, the failure rate went sky high. Joe was pissed off if the Red Sox lost, and he didn't pass as many parts on those days. That was when they realized they needed something more systematic than a guy named Joe at the end of the production line. And so when we measure our roughness, it's great to do it with a thumb, and you can do a great spot check, and you can learn a lot that way. But there's other ways that you can do it. One of the first things that we learned how to do in measuring roughness after our thumbs was, you guys probably all still know what a record player is, because hip hop DJs use vinyl and they scratch and all that stuff, right? Is that still a thing? Is hip hop still a thing? I don't know. Anyway, but you guys all know what a record player is. And so the way it works, are we screen sharing? Let's stop the screen share. The way it works is you've got a very fine point needle. It's attached to something. There's a rough surface down here. You drag the needle across that rough surface. It goes up and down. As it goes up and down, it vibrates. And if the surface is textured just right, the sound created by the vibrations sounds like music. That's how a record player works. A stylus profilometer for measuring surfaces works exactly the same way. We've got a little tip. It's on a little cantilevered beam. We've got an electric transducer over here that's checking how much this moves up and down as it goes across the surface, measuring the signal created as we drag it across the surface, and we move it off across the surface at a known velocity. This thing goes up and down. It used to be, it was all analog circuits, and there was like little RC filters and stuff in there, and it would output numbers or light up lights on the machine. Now, with the advent of digital computers being so great, we digitally sample the signal as we go across, and we get a bunch of points. That describe the path of this needle as it went across the surface. So that's great, especially if you have like a turned part. So when we make our turned parts on the lathe, you're going to end up with a surface that looks sort of like this. As the tip of the tool goes across the surface, it has some little radius. So as the tip of the tool goes across the surface, this distance is the distance it moves in each revolution, right? So you can imagine if you zoom in tight on a turned surface, you'll end up seeing a little spiral groove from the tip of that tool as it goes across the surface. And this distance is the feed in length per revolution. And the radius at the bottom there is the radius of the tool. So this kind of profilometer is great for measuring the surface roughness of a turned surface. Has anybody ever sandblasted a surface? Or seen a surface that's been sandblasted? Or if you have a mouse, I have a mouse, but the cable is too tight, so we can't hold it up to the camera. But you see the kind of texture that's on the surface of most mice. They're plastic injection molded. The way the mold was made, and the surface of that mold transfers to the surface of the plastic when it's manufactured. It was made by electrical discharge machining. They have a big a shape that looks like the mouse. They plunge it down into some really hard steel, but they're applying a current across the electrode that they're plunging down and the piece of steel. As it gets close, it makes sparks. The sparks are hot enough to vaporize the metal goes away. You pull it away, you bring it back down, it makes sparks. Pull it away, you bring it back down, it makes sparks. Pull it away, you bring it back down, it makes sparks. Eventually, you get the shape of your die in the hard steel with this electrodischarge machining. That surface that it makes isn't like a turned surface where you get a nice little spiral that goes across the part, right? That surface has 3 dimensions. Could I use this machine to measure 3 dimensions? Right now, we've got a pretty good representation of 2 dimensions. Could I measure 3 dimensions with it? I can. I measure 2 dimensions, move over a little bit. I measure 2 dimensions, move over a little bit. I measure 2 dimensions, I move over a little bit. I could build a 3D raster scan of the surface. That would be slow. So beyond the record player stylus here to measure surfaces and beyond our thumbnail, they have optical microscopes or laser scanning microscopes that can quickly raster scan with a laser height sensor. It's similar to the lasers they use at the barcode readers at the store. But it scans across, it can measure the height, moves over, measures the height, moves over, measures the height. And so this measurement of a surface is really like measuring, it's really like a 3-dimensional map of a bunch of height values arranged in a grid that we've measured.
Time check, Professor.
Yes. Go ahead.
No, I said time check.
Yeah, I saw we were at time.
Okay.
So surface topography, let me see. All right. I'm going to just quickly go back to the screen share for a second and then we'll be done. Was there anything I was supposed to tell you? Yeah, the quiz is posted. I did not put in the question that I promised about the engineering is like paint by numbers haiku. So I've decided to make that a discussion forum post, and you'll post your haiku in the discussion forum instead of as part of the quiz. Screen share the screen. So this is a representation of one of these 3-dimensional surfaces. I actually think this is some carpet that was measured with a scanning confocal microscope. Again, this is the sort of the diagram. You can actually, well, there are thousands of different ways that you could use the 3-dimensional data that you can get from one of these instruments to represent the surface, to make a model of the surface. There's probably over 100 different variables that have been standardized so that you could use them to talk to other people about it. This RT value is the distance, the average distance to the bottom of the valleys in the surface. So the average distance to the bottom of, from the peak, top of the peak to the bottom of the valleys. You can estimate that if you know the feed rate and the radius of the tool. Surface roughness is a function of speed. Yeah, that's the thing. This is what a typical trace looks like from one of these turn surfaces. You can see it's sort of got waviness and it's got roughness in it. And you can separate those two by doing some filtering. So you can take one signal out and just leave the other one. There's a bunch of different parameters. I'll do a short little mini lecture to go through the important stuff from here. One thing you should know is this RA, the average value of every point in the measured profile from the mean line. That is usually what machinists mean when they say roughness on a surface. It's the easiest one to measure. It's the easiest one to correlate with your thumb. So if somebody in the United States say, what's the roughness on the surface? That's the thing that they're talking about. And that RA is not very good at predicting the performance of a surface. The 3 sort of stylized surfaces at the bottom of this slide could all easily have the same RA mathematically, but they would not perform the same way in certain conditions. So I'll pick up a little bit on this topic on Tuesday next week. But I'm not going to spend too much time on it on Tuesday because we really need to get into the meat of next week's content. According to the schedule, next week will be the last time we do the Wednesday lecture. Although if there's things that if we fall behind on something, or if there's extra things that you guys want to talk about, we may add a couple extra Wednesdays as the class goes on. And I can stay on for questions if anybody has them. Otherwise, we're done for today.
Thank you.
Thank you.
Thank you.
Thank you.
Great.